we're going to look at the integer part of the future lifetime random variable. So we're going to introduce a new random variable denoted with kx, and kx is the so-called floor function applied to tx. So tx is a continuous random variable, so can take positive outcomes in continuous time. And with the kx, we're going to look at the integer part of my future lifetime. Yeah, so the kx is a discrete random variable. It's the expected number of whole years. If you take the expected value of kx, you're looking at the expected number of whole years that is lived in the future by an individual age x. And why is that interesting to look into? Because often an insurance product will pay out at the beginning of the year or at the beginning of the month or something. And if you look at a product that pays out at the beginning of the year, then the number of payments that you can expect for this individual to take place will be captured by the expected value of this kx, because then you need to know how many whole years will my individual continue to live in the future, right? So don't worry yet about these actuarial use cases yet, and that will come later on. So for now, just keep in mind, there is this curted future lifetime. It's denoted with kx, and it's the floor function applied to tx. So what I'll try to do with you is try to make sense of the probability function of kx. Yeah, so I'm going to wonder, what is the probability that kx is equal to k? So kx is a discrete random variable, and it's taking positive values. Okay, so if I want to say something about its distribution, then I need to find an expression for what is the probability that kx takes the value k. Now, if kx takes the value k, then that means, because of the definition of the floor function, that my corresponding tx will take a value between k and k plus 1, right? Because if I would draw my timeline, I'm looking at an individual who is x year old at time 0. So this is age and this is time. And I want to know what is the probability that this individual will die between age x plus k and age x plus k plus 1. So I want to know what is the probability that I'm in here. That's what this probability is capturing. Okay. So I need to know how to express this. So if you look at the timeline, you could say, well, using our previously introduced notation, that is a deferred probability of dying. Namely, you need to survive k years. And then after reaching hx plus k, I want to know what's the probability that you will die within 1 year from there. So one way to rewrite this thing is by saying it's the probability to survive k years minus the probability to survive k plus 1 years. And if you don't see that immediately, once again, I would recommend you to picture this on the line. So if you look at the probability kpx, that's the probability to go beyond age x plus k, right? And if you subtract the probability to go beyond age x plus k plus 1, right? So if you start from the blue guy, you subtract the green guy, then you're left with the area in red, right? So that's what we want to do. Now, we learned something powerful on Monday, and that was our multiplication rule. So the multiplication rule allows us to say that k plus 1 px is equal to kpx multiplied with px plus k. If you survive another k plus 1 years, then you first need to survive k years, you reach hx plus k, and then you need to survive another year. So plugging in this guy into the expression that we have over here, we'll retrieve kpx minus kpx multiplied with px plus k. I'm going to manipulate this expression and I'll retrieve something like this, which I can rewrite then as kpx multiplied with qx plus k. So this gives me, in quite a handy format, the probability function of my curted future lifetime random variable of my kx. Yeah, the probability that kx is equal to k, you can construct it by saying you first have to survive k years, and then you'll die within 1 year from reaching that age. Now, having this kx and its distribution, we're ready to calculate the expected value of the kx. And that will be the curted future, expected future lifetime of an X-year-old. So let's do that one together as well as a final step for this chapter. So I'm now interested in what is the expected value of kx. So let's move on with calculating the expected value of kx. So kx is a discrete random variable. So what you then have to keep in mind is the way how you learned to calculate the expected value of a discrete random variable. So you did that by taking a sum over all possible outcomes k that this random variable can take, and you do k multiplied with the probability that your discrete random variable is going to take this value, right? So this is, with the sum construction, the expected value of a discrete random variable. So what we learned now is a way to express this probability function for the kx. So that was kpx minus k plus 1 px. And the k can run here from 0 to, let's say, plus infinity, because the first value that the curted future lifetime variable can take is 0, right? It means that you die within 1 year from now. So if we're going to manipulate this expression, what we then see is that if k is equal to 0, then this term drops because k is 0 and this will lead to no contribution. If k is equal to 1, then I have a contribution 1px minus 2px. If k is equal to 2, then I've got a contribution 2 times 2px minus 3px, and so on and so forth, right? So if I work out this expression, what I will see then is that a lot of the terms here are gonna drop, and I will be left with 1px, and then I'll get 2px. Where do I get the 2px? Because I've got 2 times 2px minus a 2px over here, and that continues in the same way. So that is, I've got a 3px and so on and so forth. So in the end, I can express my expected value as the sum of kpx, and I'll be very careful where the k starts from 1 and goes to plus infinity. So that is the expression that I have for my curted future lifetime. And that's easy to calculate. That's the sum of my kpx's. The only comment when you're using this expression, so be very careful that you need to start with k from 1. Now, one of the things we often do is to build a connection between this curted future lifetime, so the expected value of kx, and the original complete future lifetime, the expected value of tx. Now, that's something we often want to do, so let's take that as a last step. I'm going to start from the complete future lifetime random variable tx, and I'm going to start from its expected value, which I know from what we learned so far that I need to calculate as the integral from 0 to plus infinity of tpx dt. So that's in continuous time, right? So there you're using the tpx where t can take a positive value in continuous time. So one way to approach this is by splitting this integral into intervals of length 1 year. So then I go from 0 to 1, from 1 to 2, from 2 to 3, etc. Okay, so that's one way to look at it. And a more elegant or a more compact way to write that mathematically would then be to write it down as a sum that goes from 0 to plus infinity of the integral from j to j plus 1. And then I look at tpx dt. So that's exactly the same. I'll start with j equals 0, then take j equals 1, etc., etc. Now, you may recall from other courses that if you look at this type of integral, you can approximate it using the trapezium rule. And that's something you should not know for this course, but let's just apply it here. If you look at it, we can say this is approximately equal to the sum over j of jpx plus j plus 1 px divided by 2. And what I can then do is then I can write this in full. And I could say, well, that's 0px plus 1px divided by 2. And then I'll go on with 1px plus 2px divided by 2, and so on and so forth. And this 0px, that's equal to 1, right? So if I work out this expression, I'll get 1 over 2 plus 1px divided by 2 plus 1px divided by 2 plus 2px divided by 2, and so on and so forth. So in the end, you'll find the following connection. It's 1 over 2, and then the sum over k, starting from 1, of kpx. And why is this so interesting? Because it shows us that the connection between the two kinds of life expectancies that we introduced so far, you don't see this, is that I've got the the expected value of my tx, that is equal to 1 over 2 plus the expected value of my kx. And that's an approximation that is often used in demography. Why is that? Because it's very easy, as we will see in chapter 3, to calculate this expected value of the kx, because the only thing you need is the kpx, where k is an integer. And this gives you a quick connection between the future lifetime expressed in curted years, so the complete future lifetime expected, and this gives you an elegant connection between the complete future lifetime and the one that is expressed with my curted future lifetime variable, the kx. The only thing I need to do is I need to add 1/2. So this is a connection that demographers will often use in practice.